So today what we're going to talk about is systems of two equations and two unknowns. And our goal is to learn how to find solutions to systems of two or more equations. Okay? Let's start out with a definition. A linear equation and two unknowns is an equation that can be written in the form ax plus by equals c, where a, b, and c are real numbers, and the two unknowns are x and y. Okay? The number a is called the coefficient of x, and what is b called? Good, it's called the coefficient of y. Can you see all of that on the screen? That's a question.
Yeah.
Okay. All right, a definition, a solution of an equation consists of a pair of numbers, a value for x and a value for y that satisfy the equation. So it has a pair of numbers, a value for x and a value of y. That's what a typical solution looks like. Okay, now what we're going to do is go through an example where we have to find a solution. Okay, or find three different kinds of solutions, or find its general solution. Let me talk about it. Let me move this up a little bit. So example 1, find three particular solutions of the given equation x plus 3y equals 3, and find its general solution in two forms, parameterized by x and parameterized by y. What the heck does that mean? Parameterized by x just means you have a solution. Remember, your solution is a pair. But in terms, whenever we say it's parameterized by x, we just mean everything here is in terms of x. So even y would be in terms of x. Okay, and I'll write this out whenever we write the solutions for this problem. Okay, parameterized by y means your solution is in terms of what variable? Y. Okay, very good. All right, so let's get started. So we want to find three particular solutions of the given equation x plus 3y equals 3. So what we should do is solve this for y. That's what you're used to doing. So you have x plus 3y equals 3. I'm going to slide this up some, so we'll have a little bit more room to work with. Okay? And then that gives us 3y equals negative x plus 3. Then we divide both sides by what? 3. Good. And that gives us y is equal to negative 1/3 x. What's the rest? Plus 1. You got it. Very good. Okay? So we have y. Now we want to find three particular solutions, right? So we know what y is. This is y. Now let's choose different x values to find out what the y will be, the corresponding y would be. So when x is negative 2, y is negative 2/3 plus 1, which that equals what? Is that right? Nope. Right, because it's negative what? What should that be? Negative what? Should it be negative? It should be positive. I'm trying to erase, not highlight. Okay. So here, notice that we should be substituting in a negative 2, right? Plus 1. When we substitute in a negative 2, you get what? Negative 1/3 times negative 2 is? 2/3 plus 1. 2/3 plus 1. 1 is 3/3, so you get what? 5/3. Good. Whenever we have x is 0, what's y? 1, good. Whenever x is 2, you get negative 1/3 times 2 plus 1. So 1/3, good. You get 1/3. So 3 particular solutions are 5/3, 1, and 1/3. That's 3 particular solutions. These are called particular solutions. But notice that there are infinitely many, right? There are infinitely many others, right? Because you can choose any x value, and for any x value, you're going to get a corresponding y. Does that make sense? What questions do you have? Okay, are we done with the problem? No. No, we're not. We only have part of it. It said find 3 particular solutions of the given equation, which we have done. Now it says find its general solution in 2 forms, parameterized by x and parameterized by y. So the general solution parameterized, that's an R, by x. Notice that, remember, a general solution is a pair, x, y. Everything needs to be in terms of x. So we have x, comma, what's y? Good, so we write that here, negative 1/3 x plus 1. This is what a general solution parameterized by x looks like for this problem. Now, in order to find the general solution, parameterized by y, what should we do? How do we find that? So let me just explain here. So what we did was we have x plus 3y equals 3. We want to find a general solution parameterized by y. So we solve our equation, that's boxed in green, for x, and we get x is equal to 3 minus 3y. So we now, in order to find the general solution parameterized by x, we have the pair xy is equal to 3 minus 3y, comma y. Okay? There was space on this page to continue example 1, but we finished it, so we don't need that here. Now, for example 2, I want you to find 3 particular solutions of the given equation 3x equals 5 and find its general solution in 2 forms, if possible, parameterized by x and parameterized by y. Would you like a couple minutes to try it? Okay, go for it. So for this particular problem, we're finding 3 particular solutions of the given equation 3x equals 5, and we're finding its general solution in 2 forms, if possible, parameterized by x and parameterized by y. So what we have here, remember you have 3x equals 5 or x is equal to 5/3, right? So 3 solutions you told me were 5/3, comma 1, 5/3, comma negative 1, and 5/3, comma 6. We only need 3, okay? So those are 3 particular solutions. So these are 3 particular solutions. And note, the second part said find its general solution in 2 forms if possible. So the first thing to note is there are 2 words, not just one. There is no general solution parameterized by x because there is no y for us to solve for. Okay? Now, is there a general solution parameterized by y? Yes, absolutely. There is a general solution. Parameterized by y. So we solved this equation for x. We got x equals 5/3. So what is the general solution? Good. It's 5/3 comma y. That's a y here, where y is arbitrary. Okay? The graph of x equals 5/3 is what? What's the graph of x equals 5/3? This is just me asking. A vertical line. Very good. It's a vertical line through 5/3. Okay? Okay? All right. So, now we need to note a couple of things. Finding all solutions, x, y, of a system of two equations and two unknowns is not too bad because it amounts to finding the intersection of two lines. Okay? The two lines do not necessarily intersect in a single point. The lines can be parallel. The lines can be parallel. Or they can coincide, meaning that they intersect at every point. Okay? So if you're finding the solution of a system of two equations and two unknowns, this boils down to finding the intersection of those two lines. However, you do have two other cases. You may have the case where you have parallel lines. So you may have lines that intersect. That would be your solution. You may have parallel lines. There is no solution here. Or you may have a line that coincides with another line. So they lie on top of each other like so, which means you have how many solutions? Can't hear you. Infinitely many. You have infinitely many solutions in this case. Okay? What questions do you have? So now we're going to go through an example where we illustrate the things that I just talked about here and that I illustrated here. We're going to go through an actual example. Okay? For example 3, we're going to talk about graphical ways to solve a system. Graphical ways to solve a system. I want us to graph the system and find all solutions, x, y, if possible. Would you like a minute to try it, or you want to just go over it together? Okay. So here we have x minus 2y equals -1, and then we have negative x plus 3y equals 3. Notice that we have two equations. What are your unknowns? X and y. So two equations and two unknowns. Okay? So we want to graph the two lines because we're talking about a graphical way to solve a system. So we want to graph the two lines. Do you normally graph your line in this form? What form do you normally put it in? Slope intercept? Okay, so let's solve this one for y. So I'll use green for the top one, and I'll use red for the second one. So you have x minus 2y equals -1. So that's -2y equals negative x minus 1. Divide both sides by negative 2. That gives us y is equal to 1/2 x, and what's the rest? I can't hear you. Minus 1/2? Plus 1/2. Why plus 1/2 instead of minus 1/2? Because we are taking this negative 1 and dividing it by a negative 2. Good. Okay? So we want to graph this line. What's the y-intercept of this line? Y-intercept, where does it cross the y-axis? Positive 1/2. Good. So it crosses at positive 1/2. And then you can use your slope to guide you, right? So your slope says do what? Up 1 and over 2. So you have a point there. And then you can go down 1 over 2. Okay? Are you with me? So it crosses the x-axis at what point? No. To find your x-intercept, you set what equal to 0? To find your x-intercept, what do? Set what equal to 0? Y. So you set y equal to 0. So that would give you 0 is equal to 1/2 x plus 1/2, which means 0, or negative 1/2, is equal to 1/2 x. Multiply both sides by 2. What do you get x is? X is negative 1. So that is your x-intercept. So it crosses there. And then you sketch your line. Okay, so we can call that L1, line 1. And then we want to find L2, let's call it. Would you like a minute to graph that one? Go for it. So now to graph L2, we have negative x plus 3y equals 3. What should we do? Not everybody at once. Add x. So we get 3y equals what? Or put your x plus 3, same thing. Then divide both sides by? And you get y is equal to? Sorry, say it again. 1/3 x plus 1. Good, that's a huge one. But it works, okay? So, from there, we can graph our line. What is your y-intercept? 1. And then, what's your x-intercept? Would you like to find that together? You have to talk. I can't read your minds. Okay? So, we have to find your x-intercept. We have that 0 is equal to 1/3 x plus 1, or we have negative 1 is equal to 1/3 x. Multiply both sides by what? 3, we get x is equal to negative 3. Okay? What? Are they parallel? Oh, careful. Bless you. So what can we do here? So it looks like they're going to be parallel, but let's use our slope to help us, okay? Our slope says we do what from this point? Up 1 and then over how many? 1, 2, 3. So that would be right here, right? So We rise 1 and run 3. We have that here. And then that's L2. So it looked like they were going to be parallel originally, but they're not parallel, right? Because they intersect at this point. What is that point? 3, 2. Good. They intersect at the point 3, 2. So that's our solution. The point 3, 2 is our solution. And note exactly one solution means that the system of equations is consistent. New word, consistent. Consistent means you have a solution, okay? You can also use consistent, the term consistent, when you have infinitely many solutions. Whenever there is no solution, we say inconsistent. Okay? What questions do you have? Okay. Part B. Part B, graph the system and find all solutions x, y if possible. Would you like a minute to try it? A couple minutes? Okay. Okay. In part B, we have to graph the system and find all solutions x, y if possible. What did you get for part B? Yes.
I got that they were inconsistent with their parallel.
Very good. So the system is inconsistent. Very good. Which means no solution, because these lines are parallel. Yes, I see your hand. Ask your question.
Do we have to put that it's inconsistent, or can we just put there's no solution?
No solution, but you need to know the term inconsistent, because I may ask you to determine whether the system is inconsistent or consistent. Okay? So let's actually graph these. The first one is the one from part A, right?
Mm-hmm.
It's the same one. So we can go ahead and sketch that graph. You have -1/2. Then we also had -1 here. And then we rows 1, ran 2. Okay? And then for the second one, for L2, you had -x plus 2y is equal to 3, or you have 2y is equal to x plus 3, or y is equal to 1/2 x plus 3/2. Is that what you got?
Yeah.
Okay. So that means your y-intercept is what? 3/2. Good. And you can use that to graph the rest. And you can use your slope to graph the rest, and you'll find that this is parallel. Okay? What questions do you have? Okay. Part C. We have to graph the system and find all solutions x, y if possible. Would you like a minute? Okay, go for it. They're the same, right? Or they overlap. Very good. These lines are the same. They overlap. So notice that these two lines are the exact same. L1 and L1. So we know the graph because we sketched it. This is now the third time, so I can use the same color. Okay, so notice that how many solutions are there? Very good. There are infinitely many solutions, which means for us that the system is consistent, and when we have infinitely many, we say consistent and redundant. That's an R. Redundant or dependent. Okay? And we say that because the two equations represent the same line. Okay? What questions do you have? So this is the graphical way to solve a system. Oh, you had a question? So we talked about the graphical way to solve a system. Now let's talk about the algebraic way to solve a system. There are 3 different methods that are typically used to solve a system. Okay, algebraic ways, there are 3. We can solve it by elimination, which is the most common method. We can solve by intersection, or we can solve by substitution. Typically, most people use 1 or 3. Okay? You can see more detailed explanations on page 265 of your books. So for part A, we want to solve x minus 2y equals -1 and negative x plus 3y equals 3. Notice that this is the exact same example that we did in part A of example 3, right? But this time we're going to use a different method. You already know that your answer should be what? What should your answer be for this problem? The pair 3, 2, right? You know your answer should be the point 3, 2, but now we're going to use a different method to get it. Okay? So, right now we're going to use the elimination method. So notice you have x minus 2y equals -1, negative x plus 3y equals 3. So using elimination, we're just going to draw a line under here, and we're going to add the 2 equations, add vertically. X minus x is what? 0. Negative 2y plus 3y is what? 1y, or just y. Equals what? Equals 2. Good. So you get y equals 2. Ah, here are ahs and everything. So here we use elimination. Okay, and then we add the columns. To eliminate x. You could have eliminated y, or we eliminated x here. You could have eliminated y if you wanted to, but now we know that y is equal to 2, so we can take 2 and substitute it into either equation. You don't need to substitute it into both, substitute it into either one. Which one would you like to substitute y into? The first one. Okay, so now we have x minus 2 times 2 equals -1, or that gives us x minus 4 equals -1, or x is equal to what? -1 plus 4 is 3. Good. So we get x is equal to 3, y is equal to 2, which means 3, 2 is our solution. So for part B, we have to solve the system x plus y equals 2 and 2x plus 2y equals 4. Okay? So, notice that here we cannot just add vertically, right? We have to do a little bit of work. What can we do to eliminate one of the variables? Yes?
Multiply by -2.
Multiply which equation? The first one? Yes, very good. Multiply the top equation by -2. So I'm going to rewrite the entire system. So we're going to have -2 times x plus y equals -2 times 2. And then we're still going to have the equation on the bottom is the same. And then we're going to distribute this -2 and simplify this. So we're going to have -2x minus 2y equals -4. And then we're going to have 2x plus 2y equals 4. Okay? Now when we simplify, what do we get? I heard no solution. Why are you saying no solution though?
They all cancel.
They all cancel, which is true. So -2x plus 2x is 0. So you get 0 plus 0 equals what? Not 4. -4 plus 4 is what? 0, right? So you get 0 equals 0. That's a true statement. So what does that mean? So what? This means that those equations are what? Are they parallel, I heard? Equivalent. This means those equations are equivalent. We ended up with a true statement saying 0 equals 0, which meant that these two lines are the exact same. So instead of no solution, what's your answer? There are infinitely many solutions. There are infinitely many solutions. Okay? There are infinitely many solutions. So we have that both lines are the same. -x plus 2 if you graph it. If you solve this top one, you get y is equal to -x plus 2. So you would have this is 2, and this is the line y equals -x plus 2. So you have infinitely many solutions here. And we can say our system is what? Consistent and redundant. Good. Or consistent and dependent. Either one. Excellent. What questions do you have? Okay. Do you have this or you need a second to finish? Okay. Let's look at example 5. Let's look at example 5. Example 5 says, Enormous State University's math department offers 2 courses, finite math and applied calculus. Each section of finite math has 60 students, and each section of applied calculus has 50 students. The department will offer a total of 110 sections in a semester, and 6,000 students would like to take a math course. How many sections of each course should the department offer in order to fill all sections and accommodate all of the students? Okay? So what we have to first do is identify and label our unknowns. What don't we know? What's unknown? How many sections of each, right? So that's what we have to label. So we're going to let x be equal to the number of sections of finite math. And we're going to let y be the number of sections of what? Good. Okay. Now what we're going to do is use the information given to set up our equations in the unknowns. Okay, so I'm going to shift this up just a little bit. Okay. So the information we have our students, And then we have our sections. And then we have finite math. And we also have applied calculus. And what else are we given? You got it, the total number of students in sections. Very good. Okay, so how many students do we have in finite math? How many?
50.
For finite math?
60.
60. How many sections corresponding to that? It says each section of finite math has 60 students. 60 students, how many sections? 1. Applied calculus. Number of students? 50. Sections? 1. Total number of students? 6,000. Good. Total number of sections? Say it again. 110. Good. So now we need to solve the system. Remember that finite math was represented by X, applied calculus was represented by Y. Okay? So now we're going to shift this up a little bit and we're going to set our system up. So we've already put all our information in our table. Let's write a system. Okay? So 60 X plus 50 Y equals 6,000. What's the next equation? Good. X plus Y equals 110. Very good. Okay? Now, we can make this equation easier to deal with if we don't want larger numbers. We can divide equation 1 by 10. Dividing equation 1 by 10 would then just allow us to rewrite our system as 6x plus 5y equals what? 600. So you'll have smaller numbers. That's the only advantage of doing this. Otherwise, you do not have to. You can use the other method. Okay? Now, how can we go about solving the system? Yes?
You can make it the bottom one negative 6x minus 6y equals negative 660.
Very good. So multiply equation 2 by negative 6. Very good. So that would make equation 2 become, our first equation remains the same. So we would have, I'm going to go up here and write 6x plus 5y equals 600. And as you said, with that negative 6 multiplying, you get negative 6x minus 6y equals, you said negative 660. Put that negative 6 in parentheses so it doesn't look like you're subtracting there. Okay? Now you simplify, what do you get? 6x minus 6x is 0. 5y minus 6y is negative y. 600 minus 660 is negative 60, which means y is 60. Now, if y is equal to 60, what's x? Remember, you can use either equation. You can use this equation or this equation to find out what x is. Which equation would you like to use? The second one, x plus y equals 110. So, x plus 60 equals 110, or as you said, x is equal to 50. That's right. So what you get is, you need 50 sections of what? Good. So we need 50 sections of finite math. And you need how many sections? 60 of applied calculus. Good. What questions do you have here? Okay, that's the end of section 4.1, which is systems of two equations and two unknowns.